In this video, we're going to be looking at the first part of topic 17b, which is the reactions of specific transition metals. This will be split into two parts just because there's quite a few different reactions that we need to go through, and we'll look at some past paper questions. And this is part of the IAL chemistry course from Edexcel. So we're going to be focusing on this video for the reactions of iron 2, iron 3, cobalt and copper, and specifically looking at them reacting with sodium hydroxide and aqueous ammonia. We should be able to write equations for each of these and also be able to discuss ligand exchange and the specific colour changes that we see in these reactions as well. So there are four key types of reactions of the transition metal complexes. The first one being redox, where we get a change in the oxidation number of our transition metal. We've got deprotonation, where one or more of the ligands loses or gains a hydrogen. We can have ligand exchange, where the ligands fit around the transition metal ion physically change, or a change in coordination number, which is determined by a change in the amount of ligands that are actually attached via the dative bonds. So we're going to look at each of these in a little bit more detail and then apply them to our examples of iron, cobalt and copper. So if we start with a change in oxidation number, this is where we simply have the transition metal changing from something like Fe2+ to Fe3+. And generally we will see a colour change here, because remember, this change in oxidation number will have a difference in the number of electrons, which affects the colour and the DD transitions between the orbitals. So Fe2+ is pale green, which is this one here, and the Fe3+ is yellow, which is this one here. And this reaction happens when this particular substance is exposed to air, so we get this oxidation reaction happening. The number and the type of ligands here is completely unchanged. So whether it is sulfate or water or hydroxide or ammonia, whatever the ligand is, that doesn't change. So we generally don't write equations for this because all we're doing is changing the one transition metal. So we don't have to write out a full equation to show this change in oxidation number. But we should be aware that this is a reaction that can happen. A deprotonation reaction is one of the most common reactions you will come across, and you will see this cropping up time and time again when we start to look at the individual examples. So when we add sodium hydroxide to something like copper 2 sulfate, we go from having that lovely pale blue colour that we see for copper sulfate to making a blue precipitate. So we go from our solution to a precipitate when we add aqueous sodium hydroxide. And at first it can look like a ligand exchange, but it's actually a deprotonation. So we go from having the copper attached to 6 waters, and then we add the hydroxide. And what we get is still the copper, and now we have 4 water ligands and 2 hydroxide ligands, and that is in our neutral complex. And we have 2 waters. Now it looks like here that the hydroxide is just taking the place of 2 of the waters, but what's actually happened is the hydroxide ions have removed the hydrogen from 2 of the water ligands and then converted them into water molecules. So we're actually losing a hydrogen from 2 of these 6 ligands, and we are left with hydroxide. So we're not actually getting a ligand exchange here. And if we add aqueous ammonia, we see the exact same thing happening, where we can make the same complex where we've lost those hydrogens from the waters, but this time instead of making water molecules, we make ammonium ions. But we make the same complex, which is very important. Now we do get ligand exchange reactions, and this is exactly what it sounds like, where one or more of the ligands is swapped out for something else. So when we've got that deprotonation that we just looked at for the aqueous ammonia, we've taken 2 ammonia molecules to each remove a hydrogen to convert them into ammonium. When this is added, we get this same blue precipitate. And coming from that blue solution. If we take excess ammonia and we add it in further, we can then take that blue precipitate and we can dissolve it to form a deep blue solution. And this is where we get a ligand exchange happening. And what actually happens is we make the copper connected to 4 ammonias and 2 waters. So we're swapping out 4 of the ligands with the ammonias, and we're left only with 2 waters, and that has a 2+ charge, and we make 2H2O plus 2 OH minus. So we're removing the 2 hydroxide ligands and removing 2 water ligands, and they're being replaced by the ammonia ligands, and this is a ligand exchange. So we can then see this actually happening when we start to line up our solutions. So this pale blue solution at the start is our hydrated copper. So this would be our copper sulfate, for example. Now we don't include the sulfate because the sulfate isn't actually the part that's reacting, but it's surrounded by this water and it's this pale blue solution. When we undergo the deprotonation, either with the sodium hydroxide or the ammonia, we make that pale blue precipitate. And that's the compound that we've seen previously. When we then get this excess ammonia being added, we get a ligand exchange reaction, and this gives us this deep blue solution where we get the ammonia ligands taking the place of the waters and the hydroxide. We can also get a change in coordination number, and this goes hand in hand with a change in ligand. So both of these things will have to happen. And an example is if we again take this copper 2 sulfate that's got the water ligands, this will gradually change from blue to green to yellow when we add in concentrated hydrochloric acid, and we have to do this slowly and continuously. We can't just dump it all in. And what's actually happening is the chloride ions from the hydrochloric acid are bonding with the copper in that dative bond to act as a ligand, and they are replacing the water. And as we previously said in topic 17a, chloride is quite a large ligand, so it doesn't have as much space, so it forms this tetrahedral shape instead of the octahedral that we see with the water. So this change in coordination number, we've went from 6 with the 6 water ligands down to 4 with the 4 chloride ions. And because this reaction is reversible, we can get a mixture that gives this sort of intermediate mixture. So our pale blue solution that we've seen is that same copper being hydrated with these 6 water ligands. The yellow solution at the end is the copper chlorides with the 4 chlorine ligands. And when we get this intermediate solution, this green one, it's because we have a mixture of the blue and the yellow solutions. But eventually, once we get this concentrated hydrochloric acid being added essentially in excess, and we've reacted all of the CuH2O6, we will be left with just a yellow compound. Now, some of our transition metal complexes can actually act as amphoteric substances, and in particular, we're going to look at some amphoteric hydroxides. So if you remember, if something can act as both an acid and a base, we call this amphoteric, and we learned this back in topic 14 when we were looking at acid-base equilibria. So if we take this hydrated transition metal ion, we know, and as we've seen and we will see multiple times, this can undergo a deprotonation reaction. And this is by adding a base to form this precipitate. So if I take the hydrated chromium, which is a green solution, and I add sodium hydroxide, I will make this green precipitate of chromium 3 hydroxide. This chromium 3 hydroxide can react with further sodium hydroxide, so to be in excess, and this gives you additional deprotonation happening. And this will then form a green solution, so that precipitate is dissolving. So because the chromium 3 hydroxide here is reacting with a base, it is reacting as an acid, because the sodium hydroxide, of course, is acting as our base and removing the protons, so our chromium 3 is acting as an acid. However, chromium-3 can also act as a base because it can react with acids such as hydrochloric acid. And if we have this happening here, it reacts as a base and that reacts as an acid, where it takes the proton from the acid and we go back to having that hydrated chromium. So this ability of chromium to be able to react with both acids and bases means it is an amphoteric substance. So we do need to be aware that there are some special reactions that these can undergo. As we move through the different reactions of the transition metals, we are going to be putting most of our focus onto deprotonation and ligand exchange reactions. And we will see this as we look at individual reactions. So let's start off by looking at the reactions of cobalt. So when cobalt reacts with aqueous sodium hydroxide, and it's added to this hexa-aqua cobalt 2, so this hydrated cobalt 2, that pink solution turns into a blue precipitate, where we have the cobalt being bonded to 4 water ligands and then 2 hydroxides because it has lost 2 of the hydrogens in this deprotonation reaction. And we form 2 H2O. So our water ligands have been converted into water molecules by removing these hydrogen ions. This blue precipitate will gradually change to pink when the product is exposed to air because we have an oxidation reaction happening here. But we need to know that we go from the pink cobalt, hexa-aqua cobalt 2 to the blue precipitate. When we add aqueous ammonia, we see the same reaction happening where we make this same complex. So we have the cobalt connected to 4 waters and 2 hydroxides. But this time, instead of making the water, we make our 2 ammonium ions. And this again is the blue precipitate because our complex hasn't changed here. If, however, we add ammonia in excess, that precipitate will dissolve, and this is our ligand exchange. So we have the 6 ammonias completely replacing all of the cobalt ligands. And this has a charge of 2+ because the cobalt still has that 2+ charge. And we get 4 waters and 2 hydroxides because that's the ligands that have been removed. If this new yellow solution is left standing, the oxidation number of the cobalt will change from 2+ to 3+, and this forms a darker yellow ion. And this is because it is being oxidized in air. So the oxygen in air is causing this change in oxidation number. And remember, we don't have to write out an equation for this. We just need to know that we go from a yellow solution to a dark yellow solution. We can also react cobalt complexes with HCl. So this is one of the few that you have to know and when it reacts with HCl, and this is our change in coordination number. So it's very similar to the copper. So if we take this hexa-aqua cobalt 2, which is this pink solution, and we add the concentrated hydrochloric acid very slowly, we will get a new complex of the cobalt chloride with a charge of 2-, and we've removed those 6 water ligands. And you can see that we have went from a coordination number of 6 with the water to a coordination number of 4 with the chloride ions. And despite the change in the charge of the complex, there is no change in the oxidation number of the cobalt. Remember, the water ligands are neutral, so they will balance out they will not have any charge to balance out the cobalt, whereas the chloride are negative, so the 4 chlorides have a charge of 4-, which balances 2+ with the cobalt, leaving you an overall charge of 2-. Moving on to iron 2. Iron 2 complexes can react with sodium hydroxide. Again, this is the most common reactions that we're going to be seeing with sodium hydroxide and with ammonia. And when we have this hydrated iron 2, it is a pale green solution, and we get a deprotonation reaction happening where we're left with 4 water ligands and 2 hydroxide ligands with no charge overall, and this makes 2 waters, and this is a green precipitate this time. So going from a pale green solution to a slightly darker green precipitate in this deprotonation reaction. When it reacts with aqueous ammonia, we see the same green precipitate being formed. So the iron connected to 4 waters and 2 hydroxides, and this makes those ammonium ions as well. But we're making that same green precipitate. And if this precipitate is left standing in air, very similar to cobalt, the iron changes oxidation number from 2+ to 3+ because it is oxidized in the air. And we go from that green precipitate to a brown precipitate where we get this iron 3 complex being formed. And this is known as triaqua trihydroxyl iron. So we're getting a change in our oxidation number when we leave the precipitate standing in air. For iron 3 complexes, they react in very much the same way where we make the same precipitate each time. Notice the difference here, we're having to react it with 3 moles of the sodium hydroxide, and that means that we have 3 water ligands that have each been deprotonated, and we make the 3 waters with the sodium hydroxide. And when we add the aqueous ammonia, we get that exact same complex being formed with the 3 water ligands being deprotonated, but we make this time 3 ammoniums. These are the same 2 reactions you're going to see happening very, very commonly over and over in this particular topic. The main thing that you have to know is what is the formula of the compound formed and what are the colour changes. And there'll be a summary table at the end of part 2 where you can view all of the different reactions and all of the different colour changes that you will need to know. So let's finish off looking at the first set of reactions by doing some past paper questions. So this first question is talking about copper 2 sulfate, and it tells us a little bit of information about the different reactions it can undergo. So the crystals of copper 2 sulfate dissolve in water to form a blue solution. This is the hydrated substance. So this is when we surround it with those water molecules, and we know that that is going to form a complex with 6 waters being attached, and that has a 2+ charge. When we add dilute aqueous ammonia to this solution, it will form this pale blue precipitate. This is our deprotonation reaction. So we get our precipitate losing 2 protons here, and we make this Cu H2O4 and 2 hydroxides, and that has no charge because remember the 2 hydroxides negative charges are going to balance out the copper 2+. And that same pale blue precipitate can then dissolve in excess aqueous ammonia to form a dark blue solution, and this is our ligand exchange. So we're going through each of the different steps and we swap out those 2 water molecules and 2 hydroxides for the 4 ammonias, and we're left with 2 other water ligands. And this is a 2+ charge. So you have to know the different steps and the different formulas of what you go through, and it's important that you remember how many ligands are swapped out. So with copper being a 2+, it reacts with 2 moles of the sodium hydroxide and we get 2 hydrogens being removed, whereas with something like iron 3, it reacts with 3 moles of the sodium hydroxide to remove 3 protons. And when it does the ligand exchange, it reacts with 4 ammonias. So these are very important equations that you do have to memorise. And you can see the 3 marks, 1 for each of the formulas. Now we're going to look at another question that is very similar but just done in a slightly different way. So we want to first of all complete the electronic configurations for the copper and the zinc atoms, and this is using the box notation. So notice it's talking about the atoms. So you can look up the atomic numbers on your periodic table. So copper we know is going to be atomic number 29 and zinc is going to be atomic number 30. Both of them have completely filled 3d orbitals, but copper is that exception where it only has one electron in the 4s. And zinc also has a completely filled 3d orbital, but the biggest difference is it has 2 electrons in that 4s subshell. And now we have basically the same question that we were just asked, as I said, just in a different way. So when a few drops of aqueous ammonia are added to a solution of copper 2 sulfate, a precipitate forms. And if excess ammonia is then added, the precipitate dissolves. We want to state the colour of the precipitate and the colour of the solution. So rather this time than asking for the formulas, we are looking at the colours, whereas the previous question gave us the colours and we wanted the formulas. So our precipitate is blue, and the solution is formed with the excess sodium, the excess ammonia. We have to be very specific, is much darker, so we just simply say it is a dark blue solution. We have to specify that we are getting a darker solution than we do a precipitate. And then part 2 is completing the equation. So we have that copper with the 4 water ligands and the 2 hydroxides reacting with the excess ammonia, and this makes our copper with our ammonia ligands taking the place, remember, of 4 of them, plus leaving behind 2 water ligands, and that gives you a 2+ charge, and we have to show that we've lost the 2 waters and the 2 hydroxide ligands, and of course balance it out with 4. And there you can see again exactly how the marks break down, showing that for the equation in particular, it's the formula of the complex ion, and then the rest of the equation is how the marks break down. That's everything for the first part of topic 17b, focusing on the iron, cobalt and copper complexes. The second part of this topic will focus on the remaining transition metal elements, and we'll look at past paper questions on that as well. If you've got any questions about this video, please do feel free to leave a comment below, and we hope to see you back soon.